So, good morning to all. So, in this section, we are going to discuss about uh, the power spectral density of random process. So, let's consider a random process x of t, and which has a autocorrelation function uh, r x x of tau. If it is a WSS process, such an expression is possible. Now, uh, we use the concept of Fourier transforms in the analysis of signals, and the same concept is applicable. The same concept of Fourier transforms can be used to analyze a random process and its autocorrelation function. So, when we find the Fourier transform of Fourier transform, I think you have an idea about Fourier transforms. Fourier transform of this Rxx of the autocorrelation function, which is defined as integral minus infinity to plus infinity Rxx of tau into e raised to minus I omega tau into t tau. This is the Fourier transform of Rxx of tau. This is denoted by Sxx of omega and is known as the uh, power spectrum or power spectral density of the random process. And from the power spectral density, we can find the autocorrelation function as the inverse Fourier transform, which is defined as integral minus infinity to plus infinity Sxx of omega into e raised I omega tau into d omega. So that is how we can find the power spectrum of a uh, random process and the power spectral density and the autocorrelation function from the power spectral density. Now, if you have two random processes, then we can have the cross correlation function, and if we consider or if we calculate the Fourier transform of a cross correlation function, uh, this will give the cross spectral density. It is the cross spectral density, or in short, cross spectrum. And we can have the cross correlation function from the uh, cross spectral density as the inverse uh, Fourier transform I omega tau d omega. And here, okay, in Fourier transform we have a minus sign. In the inverse Fourier transform we don't have a minus sign. And anyway, this 1 by 2 pi, that's part of the inverse Fourier transform, and here is a representation which we are going to use. In some cases, the Fourier transform is defined as 1 by root 2 pi into integral minus infinity to plus infinity f of t into e raised to I omega t dt. So anyhow, a transform and its inverse uh, expressed as a pair, and there is no issue in that. Anyway, now let us solve some problems in which we calculate the Fourier or the power spectral density of uh, process. So let's consider a WSS process for which the cross correlation function, sorry, the autocorrelation function is given by alpha square into e raised to minus 2 lambda into modulus of tau as the uh, autocorrelation function, and we have to find out the cross correlation, sorry, the power spectrum of the random process. Now the power spectrum is given by the Fourier transform, which is Fourier transform of autocorrelation function, and this is equal to, in our particular case, this is integral minus infinity to plus infinity alpha square, that's a constant, e raised minus 2 into lambda is also a constant, tau into e raised minus I omega tau d tau. Anyway, uh, the variable or the autocorrelation function contains modulus of tau, and we are integrating from minus infinity to plus infinity, and for we split it into two functions. So we take this alpha square as a common factor. Then the first integral is from minus infinity to 0. Then it is erased from minus infinity to 0. The modulus of tau is nothing but minus of tau. So it becomes 2 lambda tau into e raised minus I omega tau d tau plus from 0 to infinity. From 0 to infinity, the value of modulus of tau is nothing but tau. So it is e raised minus 2 lambda into tau into e raised minus I omega tau, then d tau. So that's equal to um, alpha square into, here we can make a simplification, minus infinity to 0 e to the power 2 lambda minus I omega into tau d tau plus from 0 to infinity e to the power minus of 2 lambda plus I omega, this way, into tau d tau. And now it is alpha square into the integral of e raised 2 lambda is a constant, I omega is also a constant as far as the integration with respect to tau is concerned. So it is e raised 2 lambda minus I omega into tau, the integral of e raised x is equal to 2 lambda minus I omega in between the limit minus infinity and 0 plus the second integral is e raised to minus of 2 lambda plus I omega divided by minus of 2 lambda plus I omega between 0 and infinity. Now applying the upper limit and lower limit, we have alpha square into, from the when we substitute tau is equal to 0, e raised to 0 is 1, so it is 1 by 2 lambda minus I omega minus the lower limit when tau is minus infinity. When tau is minus infinity, e raised to lambda minus I omega into minus infinity, so it is e raised to minus infinity, which is 0. Then plus here the upper bound is e raised to minus infinity is again 0. Then the lower bound, it is minus e raised to 0 is 1, and here we have a minus, so it becomes plus 1 by 2 lambda plus I omega. So this is equal to alpha square into 1 by 2 lambda minus I omega plus 1 by 2 lambda plus I omega. So this is the power spectral density which we are looking for, and anyway we can simplify it a little. This alpha square into, we can take 2 lambda minus I omega into 2 lambda plus I omega as the LCM. A plus b into a minus b is a square minus b square. So here it is 2 lambda square, that is 4 lambda square minus b square, that is I omega the whole square. So it is I square is minus 1 omega square. Then here we get 2 lambda plus I omega plus 2 lambda minus I omega. So this is equal to this 2 lambda and 2 lambda is 4 lambda. I omega and I omega get cancelled. So this is 4 lambda into alpha square uh, divided by 4 lambda square plus omega square. So this is our power spectrum of the random process. This is the power spectrum. So this is how we calculate the power spectrum of a random process. Now let us have another problem. Consider the power spectral density. Okay, the power spectral density S omega of a random process is given as 1 if modulus of omega is less than omega naught and equal to 0 otherwise. So this is the power spectrum of a wide sense stationary process. And what we have to calculate is the autocorrelation function. Find the autocorrelation function. So we know that the autocorrelation function is the inverse Fourier transform of power spectrum. So it is 1 by 2 pi integral minus infinity to plus infinity s omega into e raised I omega tau into d omega. So that is how we define the define the inverse Fourier transform. And now that's equal to 1 by 2 pi into the value of s omega is 1 within the interval mod omega less than omega naught and equal to 0 otherwise. So it has non-negative, non-zero value only in the interval mod omega less than, mod omega less than omega naught. So from minus omega naught to plus omega naught, the value of our spectrum is 1. Then e raised I omega tau d omega. Outside the interval minus omega naught plus omega naught, the value of s omega is 0. So we need only integrate in between minus omega naught and plus omega naught. And this is equal to 1 by 2 pi into integral of e raised I omega tau with respect to omega is I omega tau divided by I tau in between minus omega naught and plus omega naught. Now substituting the upper bound and lower bounds, we have from the upper bounds it is e raised I omega naught tau divided by I tau. This I tau is common for both, so we can take it as single factor minus e raised minus omega naught. So it is minus I omega naught tau divided by I tau. Now from complex numbers we have e raised I theta is equal to cos theta plus I sin theta, and e raised minus I theta is equal to cos theta minus I sin theta. So if you consider e raised I theta minus e raised minus I theta, it is equal to 2I sin theta. Or in other words, sin theta is equal to e raised I theta minus e raised minus I theta divided by 2I. I think you have this expression already studied in your complex analysis classes. And anyhow, this is a definition for sin theta. And here, if you rewrite it as if you take this dou outside, just rewrite it like this. We remove this dou from here and 2 from here, and this dou is shifted to here, and here the 2 is here. So this thing is 1 by tau into pi into this thing is nothing but sine of omega naught tau. So um, this is how we express the autocorrelation function, and the autocorrelation function is, if we write it in the simple form, 2 pi tau. It's a function of tau. So this is our autocorrelation function of the random process. So that is how we calculate the autocorrelation function from the power spectral density. So let us have one more problem. The spectrum of a random process is given. It is B by A into A minus mod omega if modulus of omega is less than or equal to A, and equal to 0 if mod omega is greater than A. And we have to calculate the autocorrelation function. So here the autocorrelation function is given by the inverse Fourier transform of uh, the power spectral density, and which is given by 1 by 2 pi into outside the interval modulus of omega less than a, it is 0, so we have to integrate from minus a to a. From minus a to a, it has a value b by a into a minus mod omega uh, into e raised I omega tau d tau. So just evaluate this particular integral, and that will give the required power spectral density. So it is 1 by 2 pi into here. Okay, there's a simple method. This is this b by a can be taken outside, and what remains is integral minus a to plus a minus modulus of omega uh, into e raised by omega 2 can be written as cos omega 2 plus I into sin omega 2 d 2, and this will give b by 2a pi into we can split it into two integrals, integral minus a to a minus mod omega into cos omega 2 plus I into integral minus a to a minus modulus of omega into sin omega 2 d2. Here also we have a d2. Now this is equal to b by 2a pi into If you consider the second integral, then a minus mod omega is an even function and sine omega tau is an odd function. So, okay, one more a slight difference here. We are not integrating with respect to tau. The integration is with respect to omega. We are integrating with respect to omega, not with respect to tau. So here also the integration is with respect to omega. And this function a minus mod omega is the even function of omega, and also note that sine omega tau is an even function of omega. Sorry, sine omega is an odd function of omega, and this is an even function of omega. So the product is an odd function. It is an odd function, and since we are integrating from minus a to a, if we integrate an odd function from minus a to a, its integral is equal to 0. And in a similar way, this cos omega tau is an even function of omega, and this a minus mod omega is also an even function of omega. So its product is an even function. So this function is an even function, and the integral from minus a to a f of omega d omega can be written as integral 0 to uh, a minus mod omega into cos omega tau d omega, and this one can be written as b by 2a pi into integral 0 to a. From 0 to a, the value of omega is always positive, so we can write it as a minus omega into cos omega to d omega. Now what remains is the evaluation of this particular integral, and we can evaluate it using integration by parts. So first function into uh, integral of the second function sine omega tau divided by tau in between 0 and a minus integral of derivative of the first with respect to omega. Omega is the variable of integration here, so we are integrating with respect to omega. So a minus omega, the derivative is 0 minus 1, so it is minus 1 into integral of the second d omega in between 0 and a. This is equal to b by 2a pi into when we substitute the upper limit, a minus a becomes 0, and when the lower limit sine 0 is 0, so the integral become equal to 0, and here if you take this minus outside, so it become minus of minus become plus, and what remains is integral 0 to infinity 0 to a sine omega tau divided by tau d omega, and this is equal to uh, this is equal to b by 2a pi b by 2a pi into uh, the 0 minus 0 0 plus what we have here is 1 by tau is a constant sine omega tau, the integral is minus cos omega tau divided by tau, have already a tau, so it is tau square, in between the limit 0 and a, is equal to b by 2a pi into the upper limit minus cos omega. Omega is the variable of integration, so omega is replaced with a. So a tau minus cos 0 is 1, so minus of minus becomes plus 1 divided by tau square. So when we simplify it, we can rewrite it as b by 2a pi tau square into 1 minus cos a tau. So this is our required autocorrelation function. So in this way, we can find the autocorrelation function of a function from the power spectrum, and we can find the power spectrum from the autocorrelation function. And remember one thing, there is a one-to-one correspondence between the power spectrum and autocorrelation function of process. There is a one-to-one correspondence, and if the power spectrum is known, we can find the autocorrelation function, and from the autocorrelation function we can find the autocovariance function, variance, and many other parameters. And in a similar way, we can find some parameters, some properties from directly from the autocovariance, power spectrum also. Anyway, uh, this the this is all about power spectral density of a random process. So by this, we are winding up the discussions on general random process. So in this module, so far we cover the concepts like uh, random process and its classification, discrete random process, continuous random sequence, etc. That's kind of classification, and Weier's stationary process, first order stationary process, evolutionary process. They are all classification of random process, and for a random process we calculate the mean function, the variance function, the autocorrelation function, autocovariance function, and in this class we have the expression for power spectral density. And for a WSS process, the autocorrelation function is a function of T1 minus T2, and this one can be written as Rxx of tau. And for a WSS process, mean is a constant, or it is independent of T. And these are the main points which we discuss in this particular chapter. And in the next session, we will discuss about a particular type of random sequence. That's our last module. Anyway, for the time being, we stop here. So